Esqueci um bocado, agora sim. Sorry about that, the mic was muted. So, repeating what I was saying, I'm just going to do a very small introduction to computer vision, just give you a broad idea of what computer vision is, what you can do with it today, and going a little bit back to understand from what we started at and what we have now. So let me know if you have any question during the presentation. I think we have also some time at the end for some questions. So computer vision. A sentence that could define computer vision could be, it's the ability for a computer to see and understand what it sees in a similar way to humans. So what you're trying to do is trying to mimic what humans do when they look at an image, and try to understand all the elements that are in that image. So what's the image about? If there are people or not, what types of objects are there, if it's an indoor scene, outdoor scene. So everything related to the semantics of what we are seeing is what we want to extract in computer vision. This is just a very small idea of what types of problems we usually handle in computer vision. We usually try to classify images, look at an image and try to label the image, saying if there's a cat in the image, or if it's a medical image, if that image contains some cancer or not. This is usually done by basically assigning, as I said before, a label to the image, to the complete image. Besides classification, we can also want to localize the object. So we want to classify there is a cat in the image and the cat is in some location in the image. Moreover, if we have more than one object, we might want to do object detection. We want to detect all the objects that are in the image, important objects. We might want to disregard everything that is related to the background, and also assign a label to each of those positions. So we have windows in the image and say, this is a cat, this is a ball, this is a dog, and so on. A more fine-grained detection is usually called segmentation. So we want to detect, basically, we want to classify each pixel as belonging to a different class. So in the object detection, we are trying to find the rough location of the object. In the segmentation, we want to find every pixel that is related to that object. So this is usually called semantic segmentation. How can we frame computer vision in other scientific domains or scientific areas? Computer vision is a multidisciplinary area, so it will usually takes ideas and fundamentals from different areas. Usually it's integrated within artificial intelligence, but more specifically, usually computer vision uses a technique called machine learning, and more recently, a more specific technique of machine learning called deep learning. Again, I'm not sure if you know what machine learning is and deep learning is. I'll try to do just a small introduction afterwards. Other related areas are image processing. So you might find some references to image processing. Image processing usually doesn't try to understand what is the content, the semantic content of the image. It just usually processes the images to remove noise, enhance the image, and so on. So image processing is not so much related to classification or detection and so on. Sometimes you might want to do some image processing before applying, trying to detect objects and so on. Computer graphics, why did I put computer graphics there? Although it's not directly related, I think it's an interesting relationship between computer vision and computer graphics. What do you think is the relationship between both? How can we establish a connection between both? So think of computer vision as we are trying to go from pixels, from images, to concepts, to some structure. There is an object in the position and so on. What are we doing in computer graphics? Exactly the inverse. So we are going from structure, we are going to put an object there, and we are going to generate synthetically the visual appearance of the object. So you can see computer vision as the inverse of computer graphics. And going back to the question that was in the first slide, do you think computers are better than humans at understanding images? So from the knowledge that you have right now, what do you think? No? Not at all? Sorry? Yeah. So you think it maybe in the future, yes, but right now they are still not better. Yeah. Mm-hmm. Mm-hmm. Yeah, that's partially true, and we're going to see afterwards some of these things. So it's depending on the size of the model, depending on the model and the task that we are doing, that we are performing in computer vision, they might be better. So, but I'll show you some numbers afterwards and try to discuss again. In some slides in the future, we're going to again ask this and try to understand it, if we have a definite answer for this question or not. But before going there, let's do some historical perspective on how computer vision started. This is an interesting historical milestone, let's say. So in 1966, at MIT, there was this student project that was proposed for students to do as a summer project. And they were trying to solve computer vision, let's say, in a 2-month period during the summer, using 10 students, basically. The idea was, so this is a part of the description of the project, like we have summer internships right now. This was one of the proposals. Let's try to do computer vision in 1 summer. Of course, this failed. It was not possible to do that, not in 1966 and not for a long time. But why is computer vision that hard? What do you think? Let's try to think about how we represent images. So usually we represent images as a bunch of pixels, so a grid of values. So this is highly unstructured information. We just have a grid of 256 by 256 values, and let's say we have 3 color channels. How can we pass from a matrix of numbers to a meaning, to a concept that is represented in the image? So this gap between pixels and semantics, pixels and meaning, is one of the most difficult things to do in computer vision. So how can we move on from highly unstructured data to structured data? And if you think about the possibilities of how many possible images are in just let's say a 32 by 32 image pixels with 3 color channels. So the possibility of different images that could be available is huge. Of course, most of these universe of images do not represent anything meaningful to us. It's just noise. But even within the universe of relevant images for humans to understand, there is a huge amount of possibilities. Just try to do some math. I don't know, 32 by 32 pixels by 3 color channels, each with 256 different values. So, and we are just talking about a very small image. So what is typically done to try to overcome this gap is, instead of just looking directly at the pixels, we'll try to find some structure in the image. We'll try to, I don't know, segment the object, try to find some relevant structure in the image, and try to describe the image using color features, what colors are present in the image, like doing an histogram of colors, trying to describe the shape using some, I don't know, for instance, a code that will represent the shape of the object, trying to encode the features, and by trying to find these small structures that represent the image, the content of the image, which we can call it image features, we are doing a step in the direction that we want to do. So after extracting these image features, we might afterwards try to say what is it in the image. So we can use some rules. If the object is more or less round, if it's green, we can say that it's an apple. But how many objects that are round and are green that are not apples? So we need to have more than simple rules for this. We can use templates like known images that we know of apples and try to compare those templates with the image that we are seeing. So these are simple techniques that can be used to try to understand what we are seeing in the image. An additional problem about image, as I was saying, there is a huge variability of possibility of images that are available, that could be represented. But even within classes, so an apple could have many different shapes, many different colors, so there's a lot of variability here. And then in this case, I'm excluding things like occluding part of the apple, an apple that is partially eaten, so it's still an apple, right? So we have to go further away from simple concepts like color and shape and so on. So this is one of the reasons that for a long time, computer vision was somewhat limited in the scope and somewhat limited in the results that it could achieve. Nevertheless, the typical pipeline that you'll see in computer vision systems or applications follows this, even today follows this path. We have a sensor, usually a camera. In cameras, we might talk about cameras like RGB cameras that are filming this presentation, so we'll see in colors, but you can have infrared cameras, you can have depth cameras that, besides capturing the colors that we are all seeing, it also captures the distance to objects, so the depth of the objects. I don't know, there are many different possibilities of sensors beyond the typical color image that you can acquire. So from there, we usually get pixels. If we are talking about 3D information, this is usually not a pixel, it's usually a voxel. So, but it's basically the same idea. We are quantifying the space into small elements. We can also do some filtering to the pixels, removing some noise, enhancing the image to make it easier for us to extract features, and then afterward, make the decisions. Okay. What types of applications until, I don't know, the 90s were usually successful? Typically only applications where you have controlled conditions, like industrial applications, where computer vision for a long time was called machine vision. So in these controls, when I'm talking about controlled conditions, I'm talking about controlled image acquisition. We control the lighting. We know exactly the conditions that we are applying, the lighting conditions that we're applying to acquire the images. We know the parameters of the sensor. So we know all of the, we control and know all of the parameters that we need to know about the image in order to extract depth, for instance, the distance to the object and so on. And we also typically, since this is an industrial application, there's a fixed setup. We know the scene structure. We know where the conveyor belt is, where the object is usually at. So everything is more or less controlled. And in these types of scenarios, the computer vision was successful and still is, of course, for a long time. And it was used for quality control, I don't know, checking if the production system is working well or not, and so on. So this was, I would say, for a long time, since the project that I showed you before in 1966 until the 90s. This was more or less what computer vision was able to do. what happened around the 90s that started to change things in computer vision? First, people started to explore more types of features beyond those that I was talking about, and more and better features, better in the sense that more robust to tasks that we're talking about, like classification. So instead of just describing the whole image, we will try to find parts of the image or points in the image that are possibly more relevant for detecting and describing, and afterwards making a decision using those features. One of the most well-known feature detector and extractor is called SIFT, which was proposed in 1999, I think, by David Lowe. And for a long time, this was state-of-the-art for image recognition. So we would extract these features, describe the points around the points that we detected, and then use that information to make a decision. Another important thing that was added to computer vision problems was machine learning. So machine learning is basically, I'll talk about machine learning a little bit, but in machine learning, you learn from examples. So instead of defining rules by hand, it's round, it's green, then it's an apple, we will learn these rules from examples. So we collect examples, and then the model will learn how to distinguish apples from oranges, let's say. So that's why we call it data-driven decisions. Okay. So you can think of machine learning as, instead of in the traditional programming paradigm where you give the data and you give the program, you compute something, and that's your output. In machine learning, you give the data, you give what is the correct output for that data, and the machine learning algorithm will output the program. So of course, this program is not written in any computer programming language. This is a mathematical model, but this mathematical model, this program, is what is going to be used to, whenever you give the program a new set of inputs, it will output, hopefully, the correct output. This is a very simplistic breakdown of machine learning algorithms. Machine learning can be usually split into two main tasks. Of course, there are more, but the most relevant ones for computer vision could be supervised learning, in the sense that we are giving, as I said, the images and the labels. So what is the correct class for this image or this bunch of images? And unsupervised learning, we just give the images. We don't give any associated label to that. So the machine learning algorithm will try to extract patterns from from the images. And I'm just saying images, but of course this could be any type of data. In our case, it's usually images. So there's a list of possible machine learning algorithms, either for classification or for regression. So in classification, we are assigning a label. In regression, we are estimating a value, a number. So we can say that classification is a categorical machine learning, as a categorical output. In regression, we have a continuous output. Okay? We're not going, of course, into detail into this. Some of you already know. If you don't know, I think there are many interesting courses where you can, even here at Phil, that you can enroll and learn more. So, how is machine learning integrated in the computer vision pipeline? So from the inputs, in this case our image, we extract the features, things like I showed you before, texture, color, shape, also those local descriptors like SIFT, include everything together into a big descriptor that will describe the complete image, and then make a decision. So this feature vector, this descriptor of the image, is the one that is going to be used as an input to the machine learning algorithm that will make these decisions. I would say that the first commercial application that was very successful, that integrated feature extraction and machine learning algorithms, yeah, was face detection, and it was incorporated in digital cameras around the early 2000s. So it started to appear in the commercial cameras, these green boxes that try to detect where a person is, the face of a person is. So this was an algorithm proposed by Viola and Jones. It used a very fast feature extractor, a very simple feature extractor, and then it used an ensemble of classifiers, so basically a combination of many classifiers to and very simple classifiers to classify if a given window is a face or not. So then it will use a sliding window approach. It will try to scan the complete image and try to say there's a face here, it's not a face, and so on. So as I was saying, I think this could be, this marks the initial real application with some impact on the community, at large, let's say. So in real time, so it worked in real time. We point a camera, and I would say that in 2022, this seems a bit silly. 20 years from the past, from this first proposal, it's silly because we now, of course, do this very easily. But at the time, it was really important. So I would say that until the 2000s, these are the main milestones. As I said, 1999, the feature detector proposed by David Lowe, and the first face detection framework by Viola Jones that worked in real time. There's also in 1989 a milestone there that I didn't talk about, because it was more of a curiosity by then in 1989. So Yann LeCun proposed a way of integrating feature extraction and learning into one single framework called the convolutional neural network. But it didn't work very well beyond very simple images and very controlled scenarios. Until recently, things changed. So let's try to look at performance at image classification in 2008. Okay? So what are we seeing there? So all of those curves are different computer vision algorithms. Without going too much into detail, the best curves are the ones that go that are closer to the top left corner. So if the curve goes straight up to 1 and then flattened at 1, it's the perfect algorithm. Okay, this is what we want. So these algorithms, the yellow one and the blue one, are much worse than the ones that are up there. Right? What are those circles over there? Persons. So one person that is doing image classification. So we have 4 persons there. They were shown many images, and this is their performance. So in 2008, humans were better than, much better, I would say, than computer vision algorithms, right? One important detail, the computer vision algorithms used full-scale images, so the complete resolution. The humans only use the 32 by 32 pixel image. So even using 32 by 32 pixels, humans in 2008 were much better than computers at image classification. This was a binary image classification. We are just saying that there is a car or there isn't a car in the image. Questions until now, and it's probably taking too long. I'll try to move faster. No? Okay, so going a little bit back to the convolutional neural network, this is what changed computer vision in 2012. And what's a convolutional neural network? It's basically a neural network. What's a neural network? A neural network is a biologically inspired machine learning algorithm model. So it tries to mimic what happens with the neurons in our brain. We have neurons that connect between each other with synapses. The synapses could be stronger or less strong, and depending on the strength of this connection, you have I would say that the signal that passes from one neuron to the other is more important than others. So this is what was proposed in the late 50s. The perceptron tries to mimic more or less this neuron model. So we have a node that has inputs, different connections, and we weigh these connections with different weights. So x1 will be multiplied by w1, x2 will be multiplied by w2, and so on. And the output is the linear combination of all the inputs weighted by these w's. And then we have plus some bias. After combining all of these, we usually apply a nonlinear activation function. This is what usually could be used to learn nonlinear combinations of the inputs. An important thing, these weights, W's and the B, will be learned. So we don't know what the correct values are for the weights. They will be learned from the examples that we show to the perceptron. For some time, this was kind of a revolution in artificial intelligence, but then short after, they understood that this small perceptron was not very effective for all tasks. So it was not able to, for instance, perform a nonlinear separation of data. So afterwards, it was proposed a combination of these perceptrons, called the multi-layer perceptrons. So all of these circles there are perceptrons, and they are all combined into layers. And each layer we have more than one node. At each layer, we connect to all the nodes that are in the next layer. So in this case, we have any number of outputs, and an important property of the neural network is that just using one hidden layer, so one layer in the middle, would be enough, theoretically, to approximate any function. Theoretically, because in practice, we will need an infinite number of nodes. So this doesn't work very well with such a shallow network, and that's where deep learning comes. How does the weights, so how can we learn those weights? And again, I'm just talking a little bit very superficially about the techniques. You can learn more about this afterwards. But basically, we do an iterative process, call it gradient descent, an optimization technique. We might, so since in an optimization technique, we might want to maximize or minimize some function. Since we are here, in this case, measuring errors or costs or loss, as it's usually called in neural networks, we want to minimize that error or that loss. So we want to find the smallest value of that function. Of course, we don't know the shape of the function. We are moving in the dark, let's say. Okay. So how do we move in the dark in something like this? The idea of the gradient descent is that the step that we do is proportional to the gradient in that point. So the intuition here is that we are trying to find the deepest point in our curve, in our loss function or in the cost function. So since we are trying to go to the bottom, we will try to move faster when the descent is more steep, so we can move faster. When it's going to start to get to the bottom, it's going to be a smaller step, so we move slower. So this is the only math equation that I have here. The idea is that each weight is updated by this factor, learning rate. So the learning rate is more or less like a cooling, or let's say we are moderating how much we are moving, and the derivative, so the gradient, so how steep is the descent at that point. Okay, so if the gradient is large, we will move faster, and the learning rate will moderate this step. So learning rate needs to be defined. You could use very small values for learning rate or larger. This gradient descent works well only for the perceptron. If you are talking about the neural network or the multi-layer perceptron, we will need an additional technique that was only proposed in the 90s. So the neural network was, again, just a curiosity for a long time. Only when backpropagation was proposed, it was possible to train the complete neural network. So in backpropagation, basically, the idea is that you will propagate the gradients from the output to the input. So you'll keep multiplying, you measure the loss, calculate the gradients, and backpropagate those gradients and keep multiplying until the input. Okay, and so at each step, we will update all the weights that we have in our network. There are many architectures, very many different architectures for neural networks. This is a very small summary of the summary was larger. I just cut some of the examples that were in this at this page, and this was in 2016. So over there you have the perceptron. The feed-forward network is basically a collection of perceptrons. We also have a deep feed-forward network. It's basically deep because it has many layers. Recurrent networks, because instead of just connecting to the next layer, we can connect also to the previous one, and so on. Autoencoder, where you'll try to learn without any label. Basically, you'll try to make the output as similar as possible to the input, and by that, we are trying to learn some representation in the middle. And also the deep convolutional neural network that we're going to talk about a little bit next. So after, I would say, in the last 10 years, everything is neural networks in computer vision. Probably it's a bit, I don't know, too short-sighted just to look at neural networks, but the fact is that it works, and it really was a revolution in the success of computer vision. So, and one of the reasons was this idea of deep learning. Remember what I said before, with one hidden layer, you can theoretically approximate any function. The question is that that's not possible because you would need a large, very large number of nodes. So instead of just using one middle layer, one hidden layer, you can use many layers. So by increasing the depth, you overcome this problem of needing too many nodes. So deep learning is basically very large neural networks. Doesn't have any, sounds very fancy, but it's neural networks that are very deep and very large in terms of parameters. So the second part of the computer vision revolution is related to this. Better architectures, so the convolutional neural network, better learning strategies, because in 1989, there was already a convolutional neural network that didn't work. So some tweaks were needed to make this work. A huge amount of data. In 1989, collecting images. Of course, I'm not sure, probably most of you were not born in 1989. But having 10 images to train a model in 1989 was, I don't know, very good. Because it was hard to collect images, we need to scan the image and so on. We would have to store it in very small hard drives or floppy disks and so on. So things that are that seem Stone Age by right now. But now collecting data from the internet, from the social networks and so on, from Google Photos, from Flickr, in the beginning of 2000s, it was easy. So it was easy to collect photos. Many of these photos already had some tags associated with it. So we have cheap data that was available in 2010. And the third ingredient is computational power, processing power. So many of these operations that you do in neural networks is basically matrix multiplications. And the very good hardware doing matrix multiplications are GPUs. So graphical processing units that were created to accelerate computer graphics is also very helpful to accelerate deep learning algorithms. So combining all of these three ingredients with this network that I was mentioning in the beginning, in 1989, Jan LeCun proposed this convolutional neural network, which basically the idea is that it applies convolutions. Convolutions are very common operations that we do when we try to filter images. Usually, we use a kernel or a filter that has a certain shape that is fixed. We know how to define a kernel or a filter to detect straight lines, for instance, or corners. But in this case, these filters are learned. So we say we are going to apply convolutions. Convolutions are basically the multiplication of each pixel value with the value of the kernel, and we sum everything together. So this is exactly the same thing that we do in a neural network. We multiply the weight by the input, and we do a linear combination of all the weights times the inputs. So we basically represent a convolution with a neural network node. The difference between the convolutional neural network and the multi-layer perceptron is that the multi-layer perceptron connects all the nodes to all the nodes in the next layer. And in this case, we are just looking at local parts of the image instead of looking at the complete image. This is much better because we are using much less parameters than using a fully connected layer, a fully connected network. What we are applying is basically what we call an inductive bias. We know that extracting features from images is usually done using this kernel idea, this filter. So let's incorporate this idea into the network and try to learn those kernels. So we are using the knowledge about how we typically do image analysis to learn the model. And by the way, this is more or less what our nervous system also does, our brain also does, and our eyes also do to interpret what we are seeing. So a convolutional neural network is basically a stack of all of these elements. Convolution, there's this rel I didn't talk about, but it's basically one of the activation functions that usually happens after doing some layer of a neural network. And then there's usually pooling. Pooling basically, what it does is to reduce the dimensionality of the image. So at each new layer, the idea is that we are going to learn on top of the previous features. So think of each convolution layer as a way of learning features. So the next layer will learn on top of those features. So they will be a combination of the previous features and so on. After after doing this feature extraction, we can make a decision. So the final layers, the FC layers over there, are the ones that will learn, that will classify or do the decision based on the features that we learn. So an interesting thing about convolutional neural networks, and even neural networks in general, is that if you try to understand what the nodes in each layer are learning to detect, we'll start from a lower semantic content, like detecting edges, corners, points, and so on. The combination of these lines will be a more complex object. The combination of those more complex pattern. The combination of that pattern will be a more complex pattern, and so on. So the final layers will be very specialized in detecting a very specific feature in the image. Like, it is very common to find nodes that will activate, that will basically detect a feature like an eye. So every part of the image where there's an eye, it will fire some signal saying there's an eye here. So it will be very specialized in that sense. And combining all of these features, we are moving up in the semantic level, let's say, and then afterwards we can make a decision more easily. So the main difference between machine learning and deep learning is that instead of extracting the features, as I said before, we are learning how to extract the features at the same time that we are learning how to make decisions. So you can say that we are doing end-to-end learning from images to decisions. And this is a very important thing that basically triggers the success of computer vision in the recent years. So I would say that if you get the correct architecture, if you have lots of data, there are some tricks that sometimes you need to do, some dark magic over here. You can have a successful trained model. And then when I say that it's tricky, training a neural network, a small neural network is not very hard, but when you start to go to more complex models, more complex tasks, sometimes you want to learn not only how to classify an image, but you want to do many tasks at once. A neural network can have many outputs, not only one label. So when you integrate, so a multitask neural network is very common nowadays. So integrating everything is not simple to train. Just to finalize, sorry. So I've talked about images. One important milestone also in around 2010 was this large collection of images that was open sourced. So basically any researcher could use this database of images. And from this database of image, a competition was created where you wanted to classify an image as one of 1,000 different classes. Not cat or dog, but 1,000 different possibilities. And there was 1.4 million images in this data set. And this is the performance of, so the best algorithms as the years progressed from 2010 to 2016. So the first two were basically a combination of feature extraction, like the one that I mentioned before, with some more ingredients, and then a machine learning algorithm like an SVM. So feature extraction plus machine learning. 2012 was the year where AlexNet was successful, and as you can see, there was a huge drop in the error. So basically, we are measuring here errors. The less, the better. And as the years progressed, all of the winners were convolutional neural networks. And an important thing is that depth kept increasing. So more and more techniques were used to be able to have deeper and deeper networks. Where did things change in a radical sense? There was some human volunteer. Let's say that he was a volunteer. No, I'm kidding. And his performance in this data set, I'm not sure how many hours did he spend doing this, had this 5.1 error %. So until 2014, the human was still better than any machine learning algorithm. But in 2015, this changed. So we could effectively say that in 2015, machines started to do better at image classification than humans. And the competition ended afterwards because it basically, they reached the conclusion that we don't need to do this anymore because this is a solved problem. Computers are very good at classifying images, period. So the question is, are computers really better at classifying, at understanding images? So this is a tricky question after showing the previous slide. What do you think, to conclude? And then I'll just show you some examples. The energy. Yeah, but I think the effort of but I think they are becoming more efficient at doing that as well. Any other opinion? Okay, I would say that yes and no. So that's not a really good answer. It's not a definite answer, but I think there is no definite answer here. Computers are much better than humans at doing very specific tasks. So you will never find a human better at classifying images if the model is trained well with enough examples. Because at some point, there are even some images that are not very easy to to distinguish between one class and the other, and probably humans get tired and so on. It will never, humans at this point will never be better at specific tasks. Where computers are not better than humans is at generalizing knowledge. So you can train a model, computer vision model, to be very good at a specific task, but it will be harder for the computer to generalize to other tasks, to let's say, if you now incorporate a new object, trying to learn that it's a new object and try to learn new characteristics that will distinguish that object from the other and so on. There's some progress in there, but for now, we can only say that we can create an algorithm that is better than humans for a specific task. So let's say for a very narrow intelligence, not general intelligence. So 2018, basically, these developments resulted in the ACM Turing Award, which is basically a Nobel Prize for computer science, to Joshua Bengio, Geoffrey Hinton, and Ian LeCun. So basically, it's debatable if they are really the only responsible for the success of computer vision and deep learning. They're probably not, but they were awarded this award, which basically means that it represents that enough achievements were done to make it really impactful in the society. And I just put there the more superficial application of computer vision, like nowadays you can pick up a phone and using any application, I don't know which one is the most famous one, to talk with others, and the application will detect you and will superimpose graphical elements like ears and funny noses and change the aspect of your face and so on. So this is a very superficial application, but it's an ubiquitous application that you have everywhere. And this is basically driven by deep learning and computer vision algorithms. Let me show you really fast some of the examples, some practical results of let's say state-of-the-art or near state-of-the-art algorithms. This one for semantic segmentation. So basically these are the outputs. It's going to detect the regions. Different colors means different classes, and the percentage is just the confidence that the algorithm has in detecting that if it's a person or a refrigerator and so on. A very impactful, and I would say the results are usually very disturbing at some point, is the use of GANs. GANs are, I didn't talk about GANs, it would take a lot to talk about, but GANs are generative networks, basically networks that are used to generate images, very simplistically. All of these images are synthetic. None of these persons really exist. These images were created by computers. They are really eerily, let's say, realistic, and that's one of the dark perspectives of computer vision or these recent advances, is that now it's more and more easy to generate fake data, realistically. Even not only with images, but also images with audio and even video. So it's becoming easier and easier to create fake video that looks realistic. And I just wanted to add this. So sometimes we're not just talking about application of computer vision algorithms to images. We can also apply it to different types of data, like in this case, 3D data, point clouds. So we have a 3D representation of the space. The white points are points in the 3D dimensional space that some sensor, usually LiDAR, detects, and then we can detect objects over these point clouds. This is usually what is done in autonomous vehicles. And I would say that it's, to some point, autonomous driving, it's not solved, but it's much, much closer to being solved than some years ago. And I would say that in For city scenarios, probably it's harder because, again, generalizing, it's harder for computer vision algorithms. Finding edge cases, it's more difficult. But for a normal driving situation, any autonomous driving system is better than a human driving a car. Interesting thing, you have lots of tools that are open source. So this made things easier to use. Almost all of the tools are based on Python. Opencv is, it should be around 20 years now, so it's an old library that is being improved year by year. It's mostly focused on computer vision, traditional computer vision, although it incorporates some deep learning algorithms within Opencv. But those on the right are deep learning frameworks. There are many more, but the most well-known are TensorFlow, that is developed by Google. Keras was initially developed as an additional framework to be used and to make easier to use TensorFlow and other libraries, but it's now incorporated in TensorFlow. And PyTorch is developed by Facebook and now Meta AI. Very quickly, things that we are moving faster now, incorporating, joining images with text. This is 2021. DALL-E. Basically, it was an implementation by OpenAI, which is also a well-known company in computer vision. Basically, you type some text, and it will generate an image that will follow the text. So if you say an armchair in the shape of an avocado, this is the output of the network. It starts to sound also a bit realistic in this case. You can find, if you go to the DALL-E webpage, you'll find more examples. And an important challenge, we need to do, besides multimodality, we need to have more efficient learning algorithms. We need to learn with less labels because labeling is something that is very costly. And one of the possibilities is doing self-supervised learning. Basically, the computer, the algorithm will look at images and will try to do some transformation, well-known transformations to the image, and try to learn from those transformations and not from the labels that we give to the learning process. And from there, it's easier to learn a better model. Okay, so that's it. Sorry for the extended time. I hope it was helpful. There's a workshop about computer vision afterwards.
There's a workshop starting at 11, so.
So if you want to practice some of these things.
So we have no time for questions now. Sorry.
But you can ask questions to the others. So thank you.
Maybe outside the top of line. Which, for those of you that are in the workshops, there's that next. You can already use on the website there's an app. You can just follow us. We're going up there now. We really have to leave the room now.
Yeah, sorry. I really